Hello students, welcome back to my channel JP Physics. In last lecture we have discussed about the analogy between mass and moment of inertia, and we comes to know the new term in rotational motion, that is moment of inertia. In this lecture we are going to derive the expression for moment of inertia of a disk. For that we have to consider one disk with uniform mass distribution, or you can say uniform disk. Of that disk we have to find out the formula for moment of inertia. See, moment of inertia, axis of rotation, we are going to consider that is passing through the center of the disk and perpendicular to its plane. If I consider this as a disk, it is rotating about an axis passing through its center and perpendicular to its plane like this. If this is axis of rotation, this disk will rotate like this. Right one. Then this axis of rotation is perpendicular to its plane and passing through the center. So let us consider one disk with radius r, capital R, and axis of rotation is passing through its center and perpendicular to its plane. Here we are going to consider negligible thickness of this disk. This disk having negligible thickness. Okay, very thin disk. Now, this R is the radius. This is rotating about axis passing through its center. Let us consider this center as O. Assume that capital M is the mass of this disk. If we are considering this disk is uniform, that is mass is uniformly distributed throughout the disk. Here we will introduce a new term, or the term that is surface density, because we are considering the uniform mass distribution. So this constant term, that is surface mass density, we have to consider here in this derivation, and that the term, it is called as a sigma, that is surface mass density, or simply you can say surface density. It is given by mass upon area. Mass upon area. Then what is we have considered here? Mass, it is capital M, and area will be pi r square. As this disk is circular, area will be pi r square. M upon pi r square is nothing but the surface density. Now, to find out the moment of inertia of this disk, we have to consider this disk is made up of a number of rings of different radius. That is, radius is going on increasing from center to the extreme. Like that, we will consider one ring like this. One ring of width dr. If I consider this width as dr, okay, and let mass of this ring as dm, small mass, that is dm. This ring is of radius small r. Radius of this ring as a small r. See, number of rings will be there. The size of ring will goes on increasing from center to the extreme. That is, range of that radius will be 0 to capital R. And in this we have to integrate the moment of inertia of the ring 0 to R, and we will get the moment of inertia of whole disk. For that only we are going to consider the moment of inertia of this ring first. We will integrate that derivation, or we will integrate that term to get the moment of inertia of whole disk. Are you getting? So first I have to consider the moment of inertia of ring. What is the formula for moment of inertia of ring? See, if this is as a ring having radius capital R, and axis of rotation is passing through its center and perpendicular to its plane. Okay, and whole mass of this ring is distributed at same distance from the axis of rotation. If there is one ring, and if I consider the axis of rotation passing through its center, then total mass of that ring is distributed uniformly at same distance from the axis of rotation. Right one. If I consider small mass dm is present at distance r from the axis of rotation, then what will be the formula for this mass which is present at distance r from the axis of rotation? That will be dm into r square, right? What is the formula we have derived in last lecture for moment of inertia? It is nothing but summation mi ri square, right one? Mass into square of the distance from axis of rotation of that mass, right one? So that formula is mr square. So mass of that particle or mass of that small element of the ring, it is dm, and its distance is r. Therefore, by formula, what will be the moment of inertia of this mass? It will be dmr square. Why? Because it is present at distance r from the axis of rotation. But I want the moment of inertia of the whole ring, right one? So I have to integrate this. I have to integrate this small moment of inertia due to this small mass dm, right one? But here r is the constant quantity. It will come out from the integration sign. Therefore, r square will be outside of integration and integration of dm will remains here. Means it is the integration of mass dm, 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 dm. All these masses are present at same distance r from the axis of rotation. Therefore, r square will be outside of that integration. It is not variable. It is constant. Right one. Then what will be the integration of dm? That will be the whole mass of the ring. If I consider this whole mass as a capital M, then the moment of inertia of ring will be mr square. Right? Mass is distributed at same distance from the axis of rotation. Therefore, integration of this dm, if we add all these masses, then we will get the mass of the ring, whole mass of the ring, or mass of whole ring, you can say. So, what will be the moment of inertia of a ring? It is nothing but mr square, right? So, here we want the moment of inertia. If moment of inertia of this ring, we want this mass dm of that ring, right? But here we considered surface mass density. This is the constant term for this disk because uniform mass distribution. We have considered uniform disk. So this sigma is not going to change for this ring also. So what will be the sigma if I consider that ring of width dr? That will be mass upon area, right? Mass is dm. And what will be the area of the ring? Area of ring. What is the formula for area of ring? It will be, you know that, circumference into width, 2 pi r dr. What will be the area of this ring? That is 2 pi r, small r. Circumference of that ring into its width. That will be the area. So, that will be 2 pi r circumference into its width, that is dr. This is the area of the ring. Then this term, that is dm upon 2 pi r dr, is nothing but the surface density. This m upon pi r square and this dm upon 2 pi r dr will having same value because we consider uniform mass distribution. This disk is uniform disk. Mass is distributed uniformly. So surface density is not going to change at any point of that ring, of that disk. Okay. Now, let us consider the moment of inertia of that ring as a di. And what will be the formula? That di will be dm into r square, right? R is the radius. All this mass is distributed at distance r from the axis of rotation. Therefore, formula for moment of inertia of the ring is dm into r square. If I want moment of inertia of that whole disk, if I consider it as I, then I have to integrate this dm into r square from 0 to r. Right one, from 0 to r. This integration will be from 0 to r. Then you will say, what about this dm? We are going to put this value of dm from this derivation. of this derivation or of this term, that is sigma is equal to dm upon 2 pi r dr. What will be value of dm there? Dm will be this 2 pi r dr will get multiplied with this sigma. Therefore, sigma into 2 pi r dr, right? So we can put this value here in place of this dm, and we will integrate this dm r square in between the range 0 to capital R, because ring will be of size, see, the size of ring will goes on increasing from this center to extreme, that is 0 to R, capital R. So let's put that value of dm here, 0 to R. What is the value? Sigma into 2 pi r dr into r square. The constant terms are 2 pi and sigma. Take it out. So, sigma into 2 pi and integration will be r cube. This r square and this r will be r cube into dr. What will be that integration? See, 2 pi into sigma, and integration of this r raised to 3 will be r raised to 4 divided by 4. Right? You know this formula now. Add 1 in this power and divide by that power only. Okay. So, r raised to 4 divided by 4 from 0 to r. Now, 2 pi. What is the value of sigma in terms of capital R? Why I am taking in terms of capital R? Because we have taken that limit from 0 to capital R. And now we have to put that value of capital R here. See, we will put that value or put limit, and then we will put the value of sigma. See, what will be this value? R raised to 4 by 4. We have to put up here upper limit, that is capital R. Formula will become r raised to 4 divided by 4, 0. Here we have not to put minus, we have to put this value, lower limit of this r, that is 0. So, it is not needed. 2 pi sigma r raised to 4 upon 4. Now, put this value of sigma here. 2 pi into, what is the value of sigma? It is m upon pi r square into r raised to 4 upon 4. Pi get cancelled. 2 2s are 4. R square will get cancelled, and here only r square will remain. What will be the last value? It is nothing but, I will write here, m r square by 2. And this is the formula for moment of inertia of a disk about an axis passing through the center perpendicular to its plane. That is mr square by 2. And what was the formula for ring? It was just mr square. Here mr square by 2 means you can understand from both this derivation that moment of inertia decreased. Why it is decreased? See, this whole mass of the ring is distributed at distance capital R only. But in case of disk, this mass is distributed throughout this area. Here, 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 here. Whole mass is not at the extreme position. From the center, distance goes on increasing, but that mass is distributed in that whole part of area pi r square. So, whole mass is not distributed at that maximum distance r, but that distance goes on increasing, means at say some small distance, then again distance goes on increasing. Throughout that area mass is uniformly distributed. But in case of ring, whole mass is distributed at same distance, that is r. Means as r goes on increasing, moment of inertia goes on increasing, because our formula is mi ri square. If r is more, moment of inertia is more. Right one. Here r is changing from 0 to r. Therefore, moment of inertia decreases compared to moment of inertia of ring. See, moment of inertia of ring is mr square, but moment of inertia of a disk is mr square by 2. You understood this derivation? We have to consider first surface mass density or surface density, that is mass per unit area, that is capital M upon pi r square. R is the radius of the disk. To derive this expression, we have to consider disk is made up of number of rings. which having different radius from 0 to capital R. From that, one ring we have considered which having mass dm, width dr, and radius as a small r. From that, what will be the surface density formula for surface density? Why I am saying formula for surface density? Because this sigma and this sigma will be same as mass distribution is uniform. At any point, surface mass density will be constant. Therefore, by considering ring, this surface density will having formula dm upon 2 pi r dr. 2 pi r dr is the area of that ring, that is circumference into width of that ring. Therefore, dm will be sigma into 2 pi r dr. Here, moment of inertia di will be dm into r square by the formula mi square. Right one? If I put the value of this dm, that is sigma into 2 pi r dr, that limit we are going to take from 0 to r, we will get that integration as r raised to 4 by 4. If we put the limit, that formula will be 2 pi sigma r raised to 4 upon 4. Here you have to remember, we have to put the value of this sigma is m upon pi r square, because we have converted this formula in terms of capital R. So we have to take the value of sigma in terms of capital R. That is m upon pi r square, capital R square. Then the terms which get cancelled, which are pi, 1 r square get cancelled, 2 2s are 4, 2 get cancelled, and remaining part will be only mr square by 2. So moment of inertia of a disk is mr square by 2. You understood this derivation? Okay, if you like or you understand this derivation, please like, share and subscribe my channel, and also press the bell icon so you will get the notification for next lecture. In next lecture, we are going to see parallel axis theorem. Okay, so for today, thank you.